Example 518, let's read over using some examples using the limit comparison test. We have 1, 2, 3 examples. Let's start with part A. In part A, we have a series given by a sequence of ANs, 1 over rad n plus 1. When you ignore the lower order term, that motivates defining a sequence of BNs of 1 over n to the 1/2. That'll be a P series with P equaling 1/2. A half is less than 1, therefore that will diverge. Now we want to determine what's going to happen to our given series. So we've cooked up a BN, a sequence of BN, which we know defines a divergent series. How do we do the limit comparison test? We need to compute a limit. What do we take the limit of? We take the limit of ANs over BNs. The convenient way to evaluate a quotient of quotients is to write down the quotient in the numerator and then multiply that by the reciprocal of the denominator. We find in this case that we get a limit of 1. 1 is positive. 1 is also finite. Therefore, whatever is happening with our BNs, the BNs diverging tell us that the sum of the ANs will also diverge. Okay, that's part A. If we look at part B is asking us to sum up the sequence of terms given by this guy. I've written down the second term in the numerator in a gray to say that it's lower order, so that if we were to ignore it, we would then have 2 to the n over 3 to the n, or 2 over 3 to the n. That then defines a geometric series where the common ratio is R equaling 2/3, and the test on a geometric is the absolute of the common ratio needs to be less than 1. Because we have that, we know that the series it defines converges. All right. So what do we want to do? We want to know the sum of these guys. Does that converge as well? Well, we look at the quotient of these guys and these guys. So that's here. And we compute out the limit. Again, we take the numerator, write it down, multiply by the reciprocal of the denominator, do some cancellations, some simplifications. 2 to the n divided by 2 to the n gives us 1. 1 over 2 to the n is 1/2 to the n, and then that will go to 0. 1 plus 0 is 1. And therefore, the behavior of the guy that we cooked up is inherited when we sum the given sequence. So that's here. All right. The third example is a little bit more involved, and they do 1, 2, 3 different attempts. On the first attempt, they try comparing 1 over ln with adding up 1 over n. In other words, they use for Bn a harmonic series. When they compute out the limit, they find that the limit will be 0. So they get this first part, which is the second statement of LCT. But the second statement of LCT has 2 different prongs. We have the first prong, but checking the second prong, we don't have that second prong, as we've used for Bn the harmonic series. So try 1 is done. Didn't work. So we move on to try 2. Try 1 was using a p-series with p equaling 1, so let's try a different p-value. Let's try 2. Well, when we compute the limit, we find that we get a limit of infinity. So that's a check mark. But the statement of LCT, the two prongs, the third part of LCT requires 1 and then 2, that the series we've chosen needs to diverge. And unfortunately, we don't have that, as we've used for Bn a p-series with p equaling 2, and that converges. So try 2 fails as well. When we look at these two tries, we've tried p equal 1, we've tried p equal 2. The third try is to split the difference, p equal 1, p equal 2, split the difference with p equal 3/2. And we'll find that we get 2 check marks, that the limit is 0, the limit of comparing ANs and BNs is 0, and that using p equal 3/2 for our BNs will yield a convergent series, and therefore the guy under consideration also converges. Nice.